So I welcome you all to another episode of Food Physics Mid-Year Edition, and this time we'll be discussing electrical properties of food. So many of you have been wondering what could probably be the electrical properties of food, except maybe for the fact that you know that some foods, especially the liquid ones, can conduct electricity. So let's find out. So I hope you're ready. Right, so although the pH of food is something you're most likely familiar with, and you may have an idea that since it deals with measuring hydrogen ion concentration, that it would have something to do with electrical conductivity, we won't be discussing that much here, no? Kasi probably diniscuss na yan since high school or since Chem 16 or something. So we'll just focus on the other applications. Although, if you realize your pH meter is also something that could measure conductivity, among other things, no? So the significance of the electrical properties of food are mainly in terms of being able to determine information on the composition of your food, such as estimation of moisture or determination of the presence of yeast, or even estimating levels of oxidation in food. And there are also processing methods that are based on electric heating rather, such as ohmic heating and pulsed electric fields. So not to be confused with thermal conductivity, electrical conductivity is also something that we could measure in food. And this electrical conductivity is defined as how easily current is transmitted into a material. So as you know, electric current is one of the 7 base SI units with um, the base unit in amperes. Okay, so if you're gonna parallel it to our lesson on thermal conductivity, you could consider the electrons as representing heat, voltage as being parallel to your delta T. Your voltage, as you may have known from high school, is often defined as a potential difference, which is parallel to a temperature difference. And then resistance, as you've seen in conduction, is similar to our wall thickness. So of course, it is assumed that you need to have a charge to be able to conduct electricity. Gusto ko lang po linawin, kapag kayo po ay nagsaksak ng isang electrical device um, sa isang wall outlet, the electrons only transfer the energy. They do not get consumed in the process, no? So imagine if you are let's say may sunog tapos nagpapasapasahan kayo ng balde, yung balde may lamang tubig. Yung mga electron, parang sila yung mga balde, no? Pag pinampatay nyo ng sunog, yung tubig lang yung iniitsa nyo sa apoy, hindi naman yung balde. Yung balde, babalik dun sa linya para malagyan uli ng tubig. So parang ganun lang, okay? So these are the basic factors affecting a food's ability to conduct electricity. First is the concentration of charge carriers. Kung walang charge carriers, walang conduction na magaganap ng kuryente. So examples of this are the formulation of your food and, for example, the level of salinity, charge and number of charge carriers. So we know, of course, that meron tayong mga um, atoms or molecules na plus 1 lang yung charge, plus 2 yung charge, minus 1, minus 2. So may effect po yun. Okay. Let's say sodium is positive, chlorine is negative, and so on. And then the mobility of your charge carriers, how they can move on a micro scale. So yung state nila, kaya nga in solids and liquids, of course, you have differences in electrical conductivity, similar to how they respond differently to thermal conduction of heat. And these are affected by things like the aggregate state, the molar mass, and the type of bonding. So most of you would probably have discussed Ohm's law in your high school physics. If you cannot remember much, there are a variety of videos on YouTube which you could watch to familiarize yourself. So wag kayo ma-intimidate sa dami ng equation. These are just mostly showing the interrelationships between the different variables involved in electric conduction. Okay, so in particular, although we look at the resistance or in this book's interpretation kasi iba-iba yung ginagamit na letter no sa ibang books no, and the conductance measured in Siemens. Okay, so essentially we just look at these two equations, although the others are useful as well. Alright, so in this case we can see the resistivity values of certain solutions. Some of them, of course, are food related. So as we know, when there's a higher resistivity, less current can flow for the same amount of potential difference or voltage. No? So we would want foods with lower resistivity if we want to conduct more electricity into the system. So in this case, as you can see, the lowest resistivity belongs to tap water, okay, and the highest being sauerkraut brine. So the conductivity of food in this instance is dependent on the temperature, wherein an increase in temperature generally comes with increased conductivity due in part to decrease in the viscosity of your fluid systems. This applies to, of course, both Newtonian and non-Newtonian. So, obvious naman, pag mas malabnaw, mas freely makaka-flow yung molecules and the electrons through that system. And then this is approximated by this equation over here, where the electrical conductivity is equal to the electrical conductivity at the reference temperature multiplied by a certain factor, which is involves the temperature coefficient for that material, as well as the temperature difference between the reference temperature and the temperature that you are working with. So as you can see here, halos linear naman yung relationship ng increasing temperature and the increase in the conductivity. Although of course, kung magkaiba yung slope mo, as you can see in the milk versus beer, so the milk has a steeper slope, meaning mas drastic yung increase sa conductivity with the change in temperature. So electrical conductivity is not just affected primarily by the amount of moisture. In particular, when we have plant-based foods, despite the high moisture content, example, some fruits or leaves may have as high as 90-95% moisture, but they have poor electrical conductivity because of the water being trapped in intercellular spaces. So may physical entrapment na nagaganap, so hindi continuous yung water mo. Diba? If you can imagine cells na nandun sa loob ng cells yung mga tubig-tubig, so um, electricity can't travel directly across a plant material. So if we do, however, destroy the cellular structures through, it's a thermal processing, mechanical crushing, or enzymatic activity, then we might find an increase in conductivity. So as an example, although yung bananas hindi naman ganun ka rigid yung structure niya as opposed to maybe cellulose or lignin plant-based materials, as you can see here, plant pieces, thermal conductivity versus temperature versus plant puree. So yung puree mas na-approximate niya yung sa mga liquids na linear slope, no? Although of course we could argue na yung kakaibang shape nitong graph B for plant pieces is because as you increase the temperature, let's say na-destroy din yung mga structural components doon sa banana mo. Kaya nag-approximate bigla siya ng linear later on. Although of course, compared to the puree, kahit pareho na sila ng slope, yung parang pinaka-intercept nila magkaiba pa rin. And that's why may gap pa rin sila there. For animal-based solid foods naman, mataas din ang moisture ng animal-based foods, usually around 60%. Pero, ganun din parang sa plant cells, poor conductivity pa rin dahil yung may mga muscle fibers yan, no? Muscle cells. Kahit nawala yung cell wall, may cell membrane pa rin. Okay. So, one factor affecting conductivity is the orientation of the muscle fiber directions. Okay. And since these are mostly protein-containing compounds, na yung muscles mo are mostly protein, water, and fat, you don't have carbohydrates, you have very little ash or minerals. No? So, because protein denatures at around above 60 degrees, so yung kung meron man siyang makitang linear, ma-observe na linear temperature conductivity, ay usually nasa range lang siya nitong 20 to 60 degrees Celsius. As usual, with plants, ganun din sa animal cells, destruction of the cellular structure will increase the conductivity, such as through the use of mechanical force, such as in cutting or grinding your meat, or in using enzymes that would soften your meat and change their structures. So we also have here equivalent conductivity, which is comparing different solutions or electrolyte systems. As you can see here, it's dependent on the intrinsic electrical conductivity of the solution, but they also factor in the equivalent number of ions, as you can see in this table, and the electrolyte concentration in moles per cubic meters or moles per unit volume. So based on what we can see here, an increasing electrolyte concentration as well as an increasing number of ions per mole of the electrolyte system leads to a decrease in equivalent conductivity, while of course having a higher electrical conductivity value increases the equivalent conductivity. So you may be wondering, bakit habang nag-i-increase yung concentration ng ions ko, ay bumababa yung kanyang equivalent conductivity? So, one of the reasons why is because of there's a sort of crowding that happens, as you've seen in the video a few slides back, no? And that causes interference in conduction, of course. Now what we want to see here is, take note, the x-axis is a square root of the concentration. So for strong electrolytes like say sodium chloride or most of your salt pairs that fully dissociate when dissolved. So yung conductivity nila varies inversely with the square root of the concentration, thus forming a linear graph dito sa square root of concentration versus equivalent conductivity, no? However, for your weak electrolytes, hindi niya sinusunod yung square root law. So as you can see, weak talaga siya dahil as you increase the concentration, biglang malaki yung drop doon sa equivalent conductivity. So for reference, you could just see here the difference in conductivity values for certain ions that may be related to food. And notice that there is a difference in conductivity, big difference with just a slight difference in temperature. So 7 degrees Celsius lang yung diferensya. Pero markedly parang some of this no more than 10% yung rise doon sa kanilang conductivity values. So although ions dissociate when you put them in liquid, such as dissolving salt in water, table salt, with the cataphoretic effect, what actually happens is the ions form a sphere-like grouping, such as you can see in this image. And then when you apply an electric field, such as what happens when you put your electrical conductivity measuring device. So ang nangyayari is, of course, the ions get pulled to the respective directions ng field, no? Yung positive mapupull sa negative charge, yung negative mapupull towards the positive charge ng electric field mo. Okay? And the resulting drag force on the central ion then is what we would refer to as this cataphoretic effect. So on the other hand, since, for example, if your salt dissolved in water, no, obviously, meron ding water molecules na nagsasurround sa kanila kasi nga nakadissociate nga sila, so nababalot sila ng tubig. And we know that these water molecules, with their asymmetrical shape, have a side that's somewhat positive and a side that's somewhat negative, no? Yung side ng hydrogen ions, yung mga plus, and yung side ng oxygen, yung minus. So these water molecules also surround the salt ions, dissociated salt ions, okay? And this causes an additional drag force when it is being pulled by an electric field, okay? So which means kung wala yung drag force na yun, edi mas madali sana silang hatakin. And this is what we call the electrophoretic effect, okay? Yung drag force caused by the solvent molecules on the dissociated ions. Sounds familiar? I think you've done yung electrophoresis, no, sa chem ninyo, so medyo babalikan natin yun ng konti. So I'm not sure if you were able to do this face-to-face or kung nakagawan kayo ng alternative experiment for this, but that is the principle behind when we do yung gel electrophoresis, no, that we place molecules in a gel and we expose it to an electric field. And because of the differences in their mainly electrical properties, nagkakaroon ng differences dun sa rate at which the proteins in this case move from one end to the other noong iyong setup. And thus you are able to determine the properties of whatever sample you have based on the profile niya doon sa electrophoresis setup mo. So conductivity is also frequency dependent. Okay, so for example, when you place an electrolyte solution into an oscillating electric field, okay, such as alternating current, so the drag force actually decreases with increasing oscillation frequency, and it would therefore lead to an apparent increase in electrical conductivity, which would otherwise not have been observed. So when it comes to the temperature dependence of equivalent conductivity, this is somewhat indirect, but your electrophoretic and cataphoretic effects are viscosity dependent. However, viscosity, as we know, is temperature dependent. And therefore, when we combine these two, we could say that yun nga, the equivalent conductivity is thus in turn temperature dependent, as we can see here. So may temperature coefficient tayong ginagamit. So for example, for each 1 degree Celsius or 1 Kelvin increase in the temperature, the equivalent conductivity of water would change by this factor or equal to about 5.8%. So as you recall from the video earlier on the measurement of electrical conductivity, so actually yung pH meter mo could be used to measure conductivity as well, no? Kung nakikita nyo doon, meron siyang mode of measurement na hindi lang pH, no? So again, you're mostly familiar with that. So you immerse the probe into your solution, and the probe has a positive and negative electrode, and then also usually some sort of temperature sensor either built into the probe or as a separate probe. And then as you saw in the video, you either measure the resistance or conductance of the liquid through various means. Okay, so and as mentioned earlier, usually meron tayong reference temperature na 25 degrees C, and we just adjust based on the actual temperature of measurement. May correction factors tayo. So again, just like in your pH meters, unless you have something like an auto temperature correction built in, the displayed values would be adjusted for what it would have been at 25 degrees Celsius. Okay, and that's important na calibrated din yung temperature ng inyong pH meter or electrical conductivity meter. Then as mentioned before, we can use a dynamic oscillating field to minimize the cataphoretic and electrophoretic effects in your measurement. And this is done through the application of oscillation from 1 to 500 kilohertz na pag-change ng direction ng field. So you may also have heard of the term impedance, which is simply defined as the resistance to the oscillation in the presence of an alternating magnetic field, which would obviously be of use for us when we are using oscillating magnetic fields. This impedance is based on three major factors: the impedance of the resistor, inductor, and capacitor of your system, and each of these are interdependent on other factors. Okay, so resistance, the frequency of the oscillation, the capacitance, and the inductance. So in terms of electrical conductivity ranges, take note this is different from equivalent electrical conductivity. Ito yung K. Okay. So as you can see here, it will range from pure water, which is 0.1 microsiemens per centimeter, all the way up to 100 to 1000 millisiemens per centimeter for concentrated acids and bases. So here are just different samples of conductivity meters. Some of them, of course, look like pH meters because some pH meters actually are also able to measure conductivity. Okay, although technically mas specific ang pH meter such that in certain conductivity meters may not be able to measure pH. So we can see here, meron ditong in typical na benchtop, we have the portable types. And this one is inline, so it measures doon sa planta sa production line mismo real time yung conductivity. So one sample application of conductivity is in measuring the oil stability index. So for example, you have a sample that's deliberately oxidized through heating at an elevated temperature, and then you pass oxygen through the sample, and the air in its headspace is collected, and of course the oxygen reacts to form oxidation products that is collected in the air. Okay, and you pass it, that collected air is passed in water again to dissolve those products, and the dissolved products are tested in the rinse water. So if you have fatty acids it increases the conductivity and therefore indicates oxidation. So, in a way, pwede mong kung controlled yung product mo and alam mo yung parang default value niya, yung changes in oxidation could be correlated to the amount of, the changes in your conductivity would indicate increased levels of oxidation that you could correlate. Okay, so one use of this test is to test the efficacy of antioxidants or packaging materials, because as we know, oxidation is one of the many forms by which certain food products degrade or in quality. Okay, so as we move on to discussing capacitance, you can watch this video in the link over here to have a graphic understanding of what a capacitor is and hence what capacitance is. Okay, so again, in summary, capacitance is the ability to store magnetic charge, and it's governed per equation by a material property called the permittivity. Okay, and its unit is the farad or coulombs per volt, which when translated to base SI units is seconds raised to the fourth ampere squared per square meter kilogram. So 1 farad is defined as the capacitance between plates of which there appear a difference of 1 volt when it is charged by a quantity equal to 1 coulomb, and 1 coulomb is the quantity of electricity transported in 1 second by a current of 1 ampere. So this may be a handful to understand, but again, we'll see ano yung silbi nito sa ating food system. So one application of capacitance is in the measurement of fluid height. So there's actually sensors that can be used to detect the level of fluid corresponding to its volume or amount through the use of capacitors. Okay, so as you can see in this illustration, there's a capacitor here, and the height of the fluid is between the height of the plates. Okay, so how do we measure this? Actually, when you have this setup, the capacitors can then be considered as a pair of parallel capacitors. So hence the equivalent capacitance would be the capacitance of the filled part and the empty part. So yung capacitor kanina, i-consider mo siya hypothetically as dalawang capacitor na nagbabago yung dimensions ng plates based on how much is empty and how much is filled. Okay, so we can translate this into an equation. Okay, like so. So yung area kanina, i-ratio mo siya dun sa part na filled by multiplying it by the height and dividing it by the distance. Okay, so you can now have two separate capacitances for the filled and empty parts. Of course, there are different permittivity values that you will be using for the empty part and the filled part. Kasi yung empty, permittivity siya ng air. Filled part, of course, then it's the permittivity of the fluid. Okay, so you can just expound these equations, and essentially we get this total capacitance to be a function of our variables. So definitely as the height changes, the total capacitance would change, okay, because both the capacitances of the filled and empty parts are dependent on the height factor. So as you've seen in the video, they normally don't make use of actual flat plates, but rather form them into rolled cylindrical sheets, no, parang sushi rolls, nori sheets, no. And in tanks, of course, you don't want a very big footprint, so the actual appearance of a device is a somewhat concentric looking probe. Pero pag tinignan mo yung loob ng probe na yun, so meron palang inner and outer electrode or plate, no? So imbis na dalawang platong side by side, meron kang inner plate and outer plate as you can see here. And of course, yung haba ng probe would depend on how high you want yung measurement mo, no? So, kasi kung ito ay fluid level height, then you want it from almost empty to up to yung full height niya. But if it's just an indicator of malapit na bang mapuno yung tangke ko, then you can have a shorter probe, okay? Alright, some of you may have wondered if we would actually treat food as part of a electrical circuit, so to speak, no? As part of itong electrical properties of food. Well, in fact, we do, and this is what we call ohmic heating. You pass current through food material to heat the food. You may have encountered ohmic heating before. Well, there's a video after the slide. So, and because you are treating the food material as a electrical conductor, then the rate of heating would depend on, among other things, the electrical conductivity or resistivity of the material instead of your typical conduction or convection. Excuse me. So in other countries, ohmic heating is currently being researched and improved. Although hindi pa siya gaanong nagagamit dun sa wide scale na production, but there have been a lot of studies on ohmic heating for various different, well, types of food, no? Especially yung isang nakita ko, which is one of my former students, nag-PhD. She also did a study on this. I think they're using it for soups na may particulate solids. And one advantage of this is, of course, possibly faster than conventional heating if you have a food that's very good at conducting electricity. And they found out, among other things, that there is lesser degradation of food quality, such as texture, color, and vitamins, because as we know, in degradation, nakakadepend siya sa time-temperature combination. And if it's a shorter time, even if it's a higher temperature, then you're more likely to preserve your nutrients in the food. Alright, so you can also watch this video about how not to wear a lab gown. I'm just joking, it's also about ohmic heating equipment for maybe pilot scale food production. So you can see how it works and also kung ano na ba yung itsura ng mga GMP compliant na slightly modern equipment, no? So we also have what we call pulsed electric field or high electric field treatment, which uses high voltage electric pulses, not mainly to heat up the food, but rather to damage cell walls to increase the permeability. And it can also inactivate microorganisms. So usually, dahil hindi nga siya pang-init talaga, it's possible use as a pre-treatment for food processing, as for example, increasing the efficiency or yield of juice extraction in mere fruits or tubers, so mostly for plant materials. Okay. So when we say high voltage, it's from 2 to 35,000 volts per centimeter. And as you can see here, may iba't iba siyang configuration based on product flow and kung ano yung flow ng electric fields mo. Okay? So pwede siyang one way, pwede siyang from the center going out, and pwede rin namang evenly spaced yung mga magnetic fields. So on the outside, here's an example of how the treatment chamber looks like. Okay, And then after this live, there will be links to two videos that you could watch for better appreciation.